Hello, welcome. This is the dipping interface. Let's look on the dipping interface, that the layer above it, and then the boundary that separates the upper layer and the lower layer of the material of the earth materials is dipping. Dipping by amount. Look for this structure. That this is the dipping layer, and this is on the ground, horizontal surface on the ground, where you have the source of the seismic waves. Then you have the receiver somewhere known as geophone. If you send these signals, they will be traveling. Let's assume the ray path for the travel for the seismic signals, they travel through the material of the upper layer. Then on reaching on the boundary, because of the difference in the acoustic impedance of these two layers, so these seismic signals will travel and they strike on the boundary, then they get reflected towards the geophone. But this layer have a dipping of angle beta. How can we get the total travel time equation for the dipping layer? Where if you have the source, you have the source on the surface, you have the receiver at a certain distance, let's say at a distance x from the source. Then when seismic signals are released, they will travel, and on striking to the boundary, they will get reflected, they will be reflected towards the geophone. Let's say in this way. How can you get the total travel time equation? Where first, from the source, draw the line which is perpendicular to the interface or the reflector. This line perpendicular to the interface or reflector, the perpendicular line. Let's say that it has the distance j from the source to the boundary or interface. The distance is the length of this path is j. Then from the surface of the interface where this line hits the normal line to the surface, then you move a distance equal to the distance from the reflector to the source. To make, let's assume this is the image, assume this is the mirror surface, then the rays from then the waves coming from the source travels and strike to the boundary, and then let's assume the image equal distance, so that the distance from the mirror surface or the reflector to the image is equal to the distance from the reflector to the object, this geometry. And let's extend this point line to meet with the line that joins to the geophone. So the wave structure will look like this one. So the rays will travel and strike and then get reflected to the geophone. Then from the source develop the line perpendicular to the interface, and then move a distance again, extend this line. Distance equals to j, which is the same as the distance from the reflector to the image is equal to the distance from the reflector to the source. And now from the source develop purely vertical line that indicates the thickness of the first layer, and let's call this is h, has the thickness h, this vertical line, and it diverges from our normal line to the reflector by the angle beta, and therefore this angle beta is the same as the dipping angle of this layer. So from the vertical line to the pure horizontal line we have 90 degrees, and therefore the angle enclosed within this entire triangle here will be the same as 90 degrees minus this beta angle, and therefore our angle will be 90 degrees minus beta. And from that you will find that you have developed the two triangles, since this distance is the same as this distance, and they share common distance, and therefore the hypotenuse of this triangle, upper triangle, is equal to the hypotenuse of the lower triangle, and this triangle is congruent to this triangle. So we can say from that figure that triangle, we're going to say that that triangle from the figure, from this figure, that the triangle DCP is congruent to triangle ACP. So triangle DCP is congruent to triangle ACP. These two triangles are congruent, and therefore this length AC is the same as length CD. Therefore AC length is the same as CD distance. So AC is equal to DC. Therefore, to get total travel distance of these seismic signals is the same as taking the distance DC plus CB, and therefore the distance that we should more concentrate is DB. So the length DB is equal to the total travel distance. Then by cosine rule from this triangle, you find that DB squared length is equal to DA squared plus AB squared minus AB times AD cosine times 2 times the cosine of this angle opposite to the side which we want to determine the length. And therefore, by cosine rule, DB squared is equal to AB squared plus AB squared minus 2 AB cosine of 90 degrees minus beta. Okay, so this is the square total travel distance. If we want to get the total travel time, total travel time squared is the same as dividing by the velocity. If you take this distance squared divided by velocity squared is the same as the right side you divide by the velocity squared, which can be symbolized v as v squared, and therefore AD squared plus AB squared minus 2AD times AB times the cosine of 90 degrees minus beta, you divide by velocity squared, and therefore T squared will be equals to, what is the value of AD or AB? Now AD is the source to geophone separation, which is x, and therefore it is x squared plus AB. AD is J plus J. AD is J plus T, therefore it is 2J. Then 2J squared minus 2x times 2J, then the cosine of 90 degrees minus beta. Okay, where but over v squared, and therefore T squared is equal to x squared plus 4j squared minus 4xj, but the cosine of 90 degrees minus beta will be the same as sine of angle beta over v squared, and therefore the travel time equation for the dipping layer is equal to x squared plus 4j squared minus 4xj sine of beta over v squared. This is the equation that describes the travel time equation for the dipping layer. Thanks for watching.